Hello, my name is Daniel Hutschenreuter. I'm a member of PTB Braunschweig, Germany, and today I'd like to give you a presentation about the importance of the International System of Units in future digital metrology. And to start with, I'd like to go back in history. Here you can see an old picture from the year 1610 of Brunswick, where PTB is today. And the city back then was a place of national and international trade. And it was a time without harmonized units. So all the people going there had their own solid measures, for example, here of length. You can see many different measures were used. And of course, to create clearness when trading on the marketplace in the city, there was a reference L, that you still can find today. Of course, this time was very difficult to measure, to trade, and the big step towards unified units and measurements was in the year 1875 with the signature of the Meter Convention by several states, and this laid the foundation for the definition of the International System of Units, at that time starting with the meter, the kilogram, and the second as international units. And of course, not only the definition of these units was needed, but a kind of organizational infrastructure to maintain this, to improve this. So also different organizations like CIPM, BIPM, and the General Conference for Measures and Weights were founded. And still until today, they improved the International System of Units. So today, we say the Meter Convention is made up by 102 member states and associated states who are jointly deciding and agreeing upon the definition of these units, which is kind of unique process in the world. If you think of international politics, and you can say that the SI units are important now for around 97% of our world economy. And one big improvement in the past years was in 2018, the redefinition of the SI units, now fully based on constants. And it said here, this is a definition now clear for all times and for all intelligent species. So it's the perfect time to also think about digitizing these units and these principles from the Meter Convention. And what we can already see, if you think of measurement, then on the national level, NMIs like PDB are providing measurements for national standards of these SI units. And they are given to industrial metrology through calibrations and chains of calibrations, allowing our products, our productions, and measures made in these productions being traceable to these national standards. On the other side, we also have the legal metrology, where we have around 150 regulated device types in Germany that are also verified according to SI units. And of course, it's PDB's mission to establish the SI units as the basis for the legal and industrial metrology on the national level. And of course, through the international organizations, CIPM, other NMIs, there is a treaty called the CIPM Mutual Recognition Agreement, MRA, where on a regular basis international comparisons are made between the NMIs to guarantee also traceability, comparability of measurements between different countries worldwide. And this allows us to do fantastic things like building international space stations where the modules are manufactured in different countries and can be put together in the space and it fits. And this should also be our example when you look at things happening here. You have read about many problems occurring there in the past decades, like the Mars Climate Orbiter was lost due to a software issue with incompatible units that were misinterpreted. And also NASA did some research. They saw the need to convert to SI of their relevant drawings, software and documents. And they found out, okay, it will cost them $370 million, and they didn't do it. So in the end, all of you, like the space shuttle mission was stopped. So we have clear international harmonized SI units that are used, that are good for manufacturing. But now when you look onto the side of software and problems occurring there, then we have still this high diversity of units and problems occurring as back 400 years ago. And so this is the motivation to say, okay, we need to sufficiently implement the international system of units and the principles from the Meter Convention into our future digital applications in industry and legal metrology. To give you an outline of my presentation, what will follow now is a short introduction to the essential challenges we may encounter when thinking of digitizing the SI. And then at the end, I also want to present to you results from two projects. One is the European SmartCom project, and the second one, called Ground Vision SI Digital Framework, is a current project on the international level of CRPM. Now, when you look at existing data like in calibration certificates, you will also find a high diversity of ways how measurement information is provided. So it's clear the situation with the units many years ago. Now we have the situation when we want to transform these data into a digital world, we have this many ways of formats, of ways how to write units and values. So we have the challenge that we have to ask ourselves, do we want to transform this historical grown chaos, there's many options, into our digital formats? And the answer, I think, here is very clear. No, we have to make this as easy as possible. So we have to find common standards to overcome this human readable way of providing information and to make it more suitable for machines to understand our data. And so the first obstacle, of course, to overcome is to say, okay, very clear, in future, if we provide a measurement value, we always have to provide it together with the unit, in the best case, the SI unit. And of course, when using SI, then the nice aspect is that it allows us to establish fundamental interoperability of our data on a machine level for quantities of the same kind. And now you also have many more future applications like the topic of dimensional analysis, where we say, or historically already Joseph Fourier said in the year 1822, we need to not only provide our quantities with units, but we also have to give them a dimension and information about dimension. And so this is important for future machines who interpret our calculations, our information in units. And here in the example, this machine tries to find out if this calculation 1 becquerel plus 1 hertz is 2 seconds to the -1. Looking at the unit only, it would be clear, yeah, this would work. But of course, all of us know that becquerel and hertz are units of quantity dimensions that cannot be added in a model. So we have to make sure that our machines in the future will be able to identify such compatible or incompatible calculations. And of course, this problem has also already been addressed. So what appeared to be impractical is to seek the knowledge on the kind of quantity only through units. So current developments even suggest to provide this information on the kind of quantity independent from the unit. So this means our second obstacle to overcome or challenge is to properly identify the kinds of quantities in our digital data representations in future. And semantic tools like ontologies, thesaurus, and so on are appearing to be suitable to achieve this by setting up unified terms to be used And through ontologies, you can also create a context, making machines able to understand when units and quantities are compatible or not. And this is also seen as a key to future better interoperability in novel applications in data science, like machine learning and so on, applied with digital data. And of course, there are more obstacles to overcome. So identification of the quantity, the unit, and the value is the first thing. Then we have to deal with the uncertainties, how we provide uncertainties. You have many different analog options, and of course we seek uniform ways in the digital formats, and our main reference is the Guide to the Expression of Uncertainty in Metrology, because this is one of the only international accepted guidelines on uncertainties. And in the broader scope, measurements, quantities are not only referenced by physical units, but you also have reference materials and reference procedures. Here we also clearly need the SI-like systems or the unified systems to provide these quantities references. And finally, implementing such metadata formats or data models for our digital exchange of measurement data is a challenge not only to single institutes, it's a challenge to the whole framework of the international metrology and the national quality infrastructure. And in the end, we need something that is universal, so applicable for many users. It must be unambiguous, not only to humans, but especially to machines when you think of these future applications like Industry 4.0. And of course, in the end, still should be easy to use. If we do not have reasonable requirements for the application of this SI in a digital world, it will not be used. Which brings me now to one of the first projects considering these very general questions. So the European MPL project SmartCom was started in 2018. The project is made up by several partners from metrology institutes in Europe, universities and industries. And the vision is to establish first basis for an unambiguous, safe, uniform communication of metrological data, especially in areas like the Internet of Things and Industries 4.0. The main outcomes that we have already are, of course, minimum requirements for such a digital data exchange in metrology. So the idea is what is universal for everybody. And the outcomes are defined as a so-called digital system of units data model, DSI. This is then closely connected to the definition of minimum requirements for digital calibration certificates. We use this digital system of units as a basis to provide measurement data. And the third gear in this project is the validation, kind of new aspect also to metrology, to say you do not only have to validate our evaluation algorithms, but also our data, the quality of our data. And I will not report about the DCC and the validation, but I give you an insight to this DSI data model. And starting and most important about this is the question, how do we implement our units? And what this project saw is, okay, units in the 9th edition of the BIPM SI brochure define a kind of unit language. So you have a programmatic approach how to define your units. And if you look into the brochure, you will find 3 elements, of course, SI units and units provided in this brochure. Then you can combine these units with prefixes and exponents to define more sophisticated units. And through additional operation of multiplication of such units, you can define all kinds of physical units that are in use today. So basically, this would be sufficient to provide units in the future. Then the next aspect of this DSI data model is the definition of minimum requirements, how to provide quantities of different kinds. Here it's shown for the real quantity. So you can see this minimum requirement to provide value and a unit, but then you can have more metadata, like a label, which is here in this case a string, a text that helps you to add this information about the dimension of your quantity, the quantity kind, and you also have information like date time, which is here provided in UTC, and all these elements of this data model are not randomly defined, but they are based on very important and international accepted standards from metrology and also computer science. Of course, this is something we call atomic, the most basic block to provide measurement data in a digital format. Then you can also add uncertainties, and here is the model shown for the expanded measurement uncertainty. And you can see that this is not only consisting of a number for the uncertainty itself, but you also have additional information on coverage factors, on coverage probability, and optional you can also give the statistical distribution. This model and similar models are also based on this guide for the expression of uncertainty in measurement. So very uniform, international accepted, universal. So this is giving you a basic outline how quantities are defined as measurement uncertainties. Of course, not everybody is using SI units. So this DSI model also provides an adapter how to provide in future quantities with non-SI units. It's called hybrid. And the principle is that you provide a list of, for example, real quantities here that all represent the same information on a measurement, but with different units. So you can think you have your measurement device providing the measure in feet on a human readable display. Then you convert it to the SI unit meter and provide the quantity in feet and meter together in your data. And in future, machines can then easily understand your data by accessing the statement referring to SI, and your users, your customers, can refer to the statement in feet, for example. Yeah, finally, I'd like to show you the link to the DCC. So most important for DCCs from our experience is that you need real quantities with these expanded measurement uncertainties. Then the DSI model does also provide lists and vectors of independent quantities, real quantities. You can also apply complex quantities and more general vector quantities as they are defined in the GAN document, and also available, but of course less common for calibration certificates, is the statement of non-symmetric coverage intervals in addition to the expanded measurement uncertainty, and of course in the multidimensional case bi and multivariate coverage regions. Yeah, finally, you will find documentation about this DSI model online if you follow this digital object identifier DOI, if you're interested to read more. Now I've come to the second project I'd like to present today, which is the CIPM, or let's say International Ground Vision on the SI Digital Framework. So in 2019 at CIPM, a project was started called the International System of Units in the Digital World. So this idea of having uniform formats for digital communication based on the SI was took up by the Meter Convention, and the task group is actually coordinating this work to establish these International System of Units in the digital world. The task group is supported by an international expert group making more technical recommendations how to do this. And the big mission is to establish really a worldwide acceptable uniform data exchange format, digital data exchange based on the SI that's not only usable for industries but also ready for our future applications in data science and artificial intelligence. Connected to this is to propose actions towards making the SI brochure machine readable and to coordinate this and to discuss this together with stakeholders all over the world. And this work is actively progress. So there's the expert group of 8 people spending more work equivalent to more than one full-time person working on this for more than 1 year. And so the next big step will be a workshop in February next year to discuss these developments, these needs for the exchange format with industry, with research, with the international quality infrastructure. And yeah, so one of the key questions at this work is, what will be the needs for digital data building upon the SI in a broader scope of metrology for industry and research, not only today, but also in 10 to 20 years. And so one of the first results of the work of the task group and the expert group is the recognition that the FAIR principles that come from the research data area are also a good starting point when thinking about future digital data for metrology. So what we need is for machines findable and accessible data that's also interoperable, so data from different sources being interoperable and reusable. So sometimes people think this means making all your data publicly available, and this is not true. You can apply FAIR principles and at the same time can maintain full control over your data, who can see it, where you put it, where you store. And now, so aligned to these FAIR principles, the SI digital framework was defined, which is basically a system of various data, services, and tools. And on the fundamental core of this framework, we have a layer that's called SI core, which provides representations of measurement data with value, unit, and uncertainty, universal to all applications. And layering upon this are then in future services using these SI core representations and further broader applications in different users domains that can establish and ensure reliability and traceability of their digital data by layering on the SI core. And some more details. So in the near term, this SI digital framework will of course contain interoperable data and metadata models for quantities and SI units, as this is the most important basic core. Then we think of digital representations of knowledge in key reference documents like the BRKM SI brochure, WIM and GAM. This will really help us to make the knowledge in our data, like the kinds of quantities, even accessible and understandable to machines. Then looking at the services, we already have data like key comparison data, CMCs, publicly provided by BRKM, the so-called KCDB database. And there's a high potential to create high quality open access points to machines to this database in the future, to also facilitate future data evaluation. And finally, most important also for this workshop, of course, the idea to adopt the DCCs as a key for traceability and metrological data is seen as very important. Of course, these are the near-term aims, so in future, many years in the future, this framework may also provide more sophisticated tools, more and more allowing our machines to do more automated analysis with the data, for example, by providing machine-readable, machine-understandable measurement procedure descriptions, analysis methods, and so on. And with this, I'd like to come to the end of my presentation. Go back to the title. So, the importance of the SI in digital metrology. So recapping, if you look at today, we expect a lot more of digital communication of data, of measurement data, and of course today this is very difficult because we as humans are used to use many different ways to provide data, different units, different number presentations, and even our different languages we use. And of course, to establish here in future a really clear, unambiguous, easy to understand communications that also machines can understand, we have truly to consider to base this communication on the international system of units and of course on these international accepted standards from the meter convention. And this will help us really when we consider this from the very beginning when defining our data formats to ensure that our data exchange in metrology, like digital calibration certificates, is fit for a future world where not only humans will need to interpret data, but more and more intelligent, smart machines, smart software will use this data to derive decisions and to improve results. And with this, I'd like to thank you and look forward to the discussion. Goodbye.